My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. Hope you are well and safe from Corona pandemic. As we know that we cannot continue our normal academic program inside the campus due to the Corona pandemic, so we have to start our online program. And our Department of Physics, Pabna University of Science and Technology, has started its online program, including International Physics webinar. We have successfully completed our 147th International Physics webinar, including two Nobel laureate speakers. So we are trying to adjust with this new normal situation. Today is very important day for our department. Today, I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, College of Liberal Arts and Science, the University of Kansas, USA. And we have with us here today Dr. Debbie J. Besson, Professor, Department of Physics and Astronomy, College of Liberal Arts and Science, the University of Kansas, USA. And he has already connected with us. So I'd like to welcome our speaker. Sir, good morning and good evening to here. Thanks for accepting our invitation, sir. And we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. So for those who are new, I would like to inform that we have divided our webinar into three parts. First of all, I would like to introduce our speaker with all of you, and then our speaker will deliver his speech. And at the end, we have a discussion session. In that time, anybody can join with us, and you can ask question by commenting. I think you have already come to know the title of this International Physics webinar, and the title is Detection of Ultra High Energy Neutrinos Using Radio Wave Techniques. And our speaker is Dr. Dev J. Besson, Professor, Department of Physics and Astronomy, College of Liberal Arts and Sciences, the University of Kansas, USA. And we can see his academic and professional career. Dr. Debbie J. Besson is currently involved in several projects seeking to detect ultra-high energy cosmic rays, primarily protons or neutrinos, from either their radio wave emissions or radar reflection, and at least one of which requires flying barbecue lighters at 38 kilometers above the Antarctic continent. Within the last several years, funded by Fulbright Foundation, the US CRDA program, and the Russian Mega Grant program, he has enjoyed a faculty co-appointment at the Moscow Engineering Physics Institute, MEPhi, and coordinated to work on medical and astrophysical application of silicon photomultipliers, as well as studies of anomalies, charm baryon correlation with the Bally and Bally 2 experiment. To the extent that any of this has been successful, it is only because he has been exceptionally fortunate to be able to collaborate with talented and industrious students who do all the real work that he takes credit for. He would like to grateful acknowledge support from the NSF, NASA, and the Cottrell Research Corporation, the University of Kansas, and the State of Kansas, the Civilian Research Defense Fund, CRDF, MEPhi, and the Fulbright Foundation, without whom he would be forced to get a real job. And you can see his professional and educational record. He completed his BSc in Physics, Columbia University from, and PhD in Physics, Rutgers University, and then professional background. Uh, from 1990 to 1993, he worked as a postdoctoral research associate at Cornell University, and in 1993 to 1996, assistant professor, University of Kansas, and then 1997 to 2001, associate professor at the same university, and from 2001 to present, he is working as a professor at the University of Kansas. Research interests cosmic rays, cosmogenic neutrinos, and Ascarian effect. Selected awards and honors. You can see his some honors and awards, and this is his research grant publications. So thanks for all of your patience. Now it's time to go to our speaker. Sir, thanks again for accepting our invitation, sir. It's your time, sir. You can start your session, sir.
Okay. Thanks very much for that very kind introduction, and of course, thanks very much for the invitation.
Yes, sir. It's our pleasure, sir.
Sorry?
No, sir. You can carry on, sir.
Okay. Yeah. So thanks very much for the invitation and the introduction. I should caution that I have a lot of slides, and I almost certainly won't get through all of them. But I'd like to at least give you a sense of the science that we're interested in, and also the experimental techniques that we're using to try and realize that science. And in that spirit, this particular slide, I think, captures the essential features that motivate the radio wave technique for detecting neutrinos. So what's shown here is a graph that is essentially showing you the range of how far you can see a particular cosmic ray source. So let's imagine, for instance, that you have a proton which is produced some distance away from the Earth. So over here on the x-axis is the distance between ourselves and some source of a cosmic ray source, for instance, a proton or a high energy gamma ray. And to give you a sense of scale, again, the units here are megaparsecs. So the scale of our local Milky Way galaxy is about 30 kiloparsecs, or about 0.03 megaparsecs. The local group of galaxies has a scale which is maybe a couple of megaparsecs, and so on and so forth. Now, on the vertical scale is the logarithm of the energy of the cosmic ray, either a proton or a photon, for instance, that you'd like to observe. And so, for instance, if there is a proton which is produced at a distance of, say, 1,000 megaparsecs, so again, the distance between the Milky Way and the nearest large spiral galaxy, namely Andromeda, is about 1 megaparsec. So if you have a proton produced at an energy of 10 to the 10th electron volts, or about 10 giga electron volts, that proton will be able to reach our observatories here at the Earth without any problem. However, if you have a proton which is produced at a distance of maybe 100 megaparsecs from the Earth, with an energy of about 10 to the 20th electron volts, that proton will not reach the Earth because it will interact with the cosmic microwave background radiation. Remember, this is essentially the faint glow of radiation left over from the Big Bang. And as the energy of the proton gets higher and higher, the likelihood that it will interact with a cosmic microwave background photon increases. Therefore, at very high proton energies, remember this is about a joule, and at large enough distances, protons will interact with the cosmic microwave background radiation, and in the process, that proton will undergo a process such as this. So proton interacts with a cosmic microwave background photon. It produces a so-called delta resonance. That delta resonance decays into a neutron and a charged pion. That pion then decays to a muon and a muon neutrino, and the muon decays into an electron and electron neutrino and a muon neutrino. So on the one hand, you have lost the proton to observation. You will never see it because the proton has interacted with the CMB background. On the other hand, you have 3 neutrinos which are somehow tracers. They have some memory of the original proton that produced them. So we can use, if we can detect these neutrinos, that can tell us something about the very high energy protons that may have produced them, may have engendered them. Similarly, the case is even worse for high energy photons. For high energy photons, at an energy of about, say, 10 to the 14th electron volts or higher, at those energies, the likelihood or the cross section for a high energy gamma ray interacting with a cosmic microwave background photon will approach the center of mass energy required for gamma gamma to observe electron positron. And similarly, in that way, you will lose the photon, this high energy gamma ray, to observation here at Earth. So the basic idea here is that the cosmic microwave background places a limit on how much astronomy we can do for high energy protons and high energy gamma rays. So the obvious question is, if you can't see high energy protons and high energy gamma rays, what objects can you see in order to do astronomy? And the answer is neutrinos. So these neutrinos have very, very low cross sections. They interact very rarely with matter. Just to remind you, it takes something like 1 light year's worth of lead to absorb neutrinos coming from the sun. And that means that neutrinos can easily penetrate the cosmic microwave background that permeates the universe. On the other hand, that is a liability insofar as it means that you have to have a very large target in order to detect the very rare times when a neutrino interacts. Okay, so the scale here is very hard to read, but this is just a plot of the cross sections for neutrinos, photons, and protons. And if you can read the scale, this is just telling you that the neutrino cross section, or the likelihood of neutrinos interacting with matter, is much, much smaller than for photons or protons. So again, photons and protons, we will not see. High energy photons and protons we will not see because they interact with the cosmic microwave background. However, neutrinos will preserve information. High energy neutrinos will preserve information from very far away, and therefore they contain information about the otherwise hidden reaches of the universe. Now, as I said before, you can compensate for the fact that the cross section is so small, the interaction likelihood is so small, by using a very large target. And the target that we use in our case is the Antarctic ice sheet. So this is a sort of a schematic, a cartoon of the various strategies that you might use in order to detect very high energy neutrinos. One is so here we're imagining there's a neutrino that comes up through the Earth. Remember that neutrinos can penetrate very large distances. They can penetrate all the way through the Earth very often. And so here's a neutrino which has penetrated through much of the Earth, but it interacts in the ice sheet. When it interacts with the ice sheet, it crashes into an ice molecule. There is a spray of debris and radiation. And much of that radiation that results from that interaction, from that collision, shows up in the form of radio waves. And Antarctic ice, it turns out, is very transparent to radio waves. The attenuation length for radio waves in Antarctic ice is around 1 kilometer. So those radio waves will travel up through the ice and exit through the air. And if you have a balloon, and at the bottom of the balloon is a set of radio wave antennas, then you can detect the radio waves produced by that neutrino interaction. Or you can, for instance, imagine that instead of having your radio wave array hanging off a balloon. Instead, you put the radio wave receiver array directly into the ice, and in that way you can directly detect the radio waves coming from a collision. And that is the strategy which is followed by a couple of the experiments that I'll talk about. All right, so there are a large number of experiments which intend to use this, exploit this idea of compensating for the very small cross section of neutrinos with a large target. The ARA and Ariana, and so Anita is the balloon-borne strategy up here. The ARA experiment is an experiment which consists of radio wave antennas embedded in ice. Ariana uses antennas which are sitting on the surface of the ice. The RNOG experiment, which has essentially the same strategy as ARA, is going to make its first deployment of radio wave receivers in May of 2021. So in fact, in about 2 weeks. I myself am going up to Greenland in July as part of this experimental effort. And there are additional experiments which also use similar strategies that I won't talk about in detail. So what I'm going to do here is I'm going to focus on the experiments that use the ice sheet as a target for neutrinos. Now, this idea originated with Markov and Zheleznyk at the Institute of Nuclear Research in Moscow in 1986, but at the time, there were insufficient funds in the Soviet Union to experimentally realize it. So it's only really now come to fruition some 35 years later. Okay. So the ARA experiment, as I said before, consists of radio wave antennas which are embedded in the ice. One of the things which is interesting is that if a neutrino interacts in the ice, there are in fact two optical solutions through which radio waves will travel from the source point to the receiver. One is a so-called direct ray, and one is a so-called refracted ray. This picture of having a direct and a refracted ray and two optical paths is essentially the same physics which results in the observation of a mirage on a dry surface on a hot summer day, if you like, at least in Kansas. All right, and as I said before, the Ariana concept uses antennas which are very close to the surface. Now, one of the things that Ariana also can see, in addition to neutrinos, in this case, there's a neutrino which is downcoming. It produces radio waves, which in fact are not going up, but are going down. And the radio waves reflect off of the underlying water layer underneath the ice sheet at the Ross Ice Shelf. And they come back up, and they are detected by these antennas. The Ariana experiment also has sensitivity to radio wave emissions that are produced when a high-energy cosmic ray crashes into the atmosphere. It's essentially the same idea. The debris from that collision includes both particles as well as radio waves. So this has become increasingly a strategy for measuring ultra-high energy cosmic rays. Now, getting back to the first slide, so what you're looking for are protons. So you can't see all the protons that are in the hatched region in the upper right, but other protons that are coming from that are less than 10 to the 20th electron volts and are created closer than at distances of, for instance, quasars, you can observe through their collisions with the atmosphere. And that is one of the strategies which is used to detect not just neutrinos, but also ultra-high energy cosmic rays interacting in the atmosphere. So this experiment can measure both neutrinos as well as, for instance, protons. All right. The Anita strategy is, as I said before, sensitive to neutrinos. And just like Ariana, it's also sensitive to so-called extensive air showers. These are radio wave emissions that come from those collisions of protons or charged cosmic rays with the atmosphere itself. Now, one of the things that's interesting is that if you imagine so let's imagine that there is a cosmic ray interaction over here. The balloon, which carries the radio wave, so this is a suite of radio wave antennas. It's looking down on the Antarctic ice sheet. So it's flying in a circle around the Antarctic ice sheet, and it's looking down, and it's looking for upcoming radio wave signals that result, as I said before, from a neutrino interaction in the ice that's producing upcoming radio wave signals. Now, in addition to that, the Anita experiment is also sensitive, as I said before, to charged proton cosmic rays, not just neutrinos, but charged protons that interact in the atmosphere. And there are basically two types of signals that can be observed. Since the balloon is flying above the atmosphere, there is a proton that can be so-called Earth skimming and can interact in the atmosphere just below the horizon. So this would be a so-called upcoming proton, cosmic ray, that interacts in the atmosphere itself, and the signals go directly up towards the balloon. The other possibility is that a proton can interact in the atmosphere, but the signals are headed down. They reflect off of the ice surface and go back up to the balloon. These two signals should be, so this is a direct ultra-high energy cosmic ray, and this is reflected. These two signals should be identical with one exception. The difference is that this signal will have a different quote-unquote polarity than this signal. So for instance, if this picture up here in green is represents the signal that you would observe for a direct ultra-high energy cosmic ray. So it's a signal that goes up and comes down, it goes back up again. The signal which is reflected would be inverted because from Physics 101, this is a wave which is reflecting from a higher, from a lower index of refraction material and reflecting off of a higher index of refraction material. And because of that, the signal will invert. And I'll talk about that in a second. So the signals that you can observe, again, are distinguished primarily on the basis of their so-called polarity. So let me go ahead and I'll just show you a couple of pictures. So this is a picture of what the balloon looks like during inflation. So what you do is on the coast of Antarctica, you fill this balloon, this mylar balloon with helium. The actual payload, so this thing in the lower left is this suite of antennas, which is shown here. So the suite of antennas is again scanning downwards and looking for radio wave signals that are coming upwards. So here is the balloon during inflation. Here is the actual payload. And this is our first flight. This is the balloon after it has been launched. So here is the mylar balloon with helium. Just as a reminder, as the balloon goes higher and higher up into the atmosphere, it will expand more and more as the ambient pressure gets lower and lower. So eventually, this helium balloon will occupy the size of a large stadium. I don't know what the biggest cricket stadium is in Bangladesh, but here in the US, the standard is something like the Rose Bowl. So it would occupy a stadium which is capable of holding something like 100,000 people when the balloon is finally at so-called float altitude of 38 kilometers. Okay, there have been essentially 4.5 flights of the Anita project, and the payloads all look the same. And perhaps the most interesting thing that Anita has announced are these so-called mystery events. And let me try to explain what these mystery events look like. So here is these angles, here are events that have been observed. And these angles represent the angle relative to the horizontal at which the incident radiation is observed. So for instance, if we go back to this slide, from the horizontal is directly across, and direct ultra-high energy cosmic rays will arrive with angles of about from 0 to -6 degrees relative to the horizon. If there is a cosmic ray which is incident on the Earth at something greater than 6 degrees, so say -7 degrees or -8 degrees, the signals from that cosmic ray will have to reflect off of the surface. So you only have 6 degrees of aperture for direct signals. Something steeper than that is a signal which has reflected off of the surface and therefore should be inverted. So here are some signals which have been observed. Here is -5.5 degrees, -3.6 degrees. These are so-called atmosphere skimming air showers, which are normal, direct, ultra-high energy cosmic rays. You see they have the same polarity. This goes up a little bit, it goes down a lot, goes up again, then comes back down. So these two signals in the upper right and the lower left have the same polarity. This is a signal at a steeper incidence angle. So this is an incidence angle which should have reflected. And indeed, this signal is just upside down compared to those two signals. Okay, this signal is at essentially the same angle as this signal. However, it has not inverted. There was one and this is called an anomalous or a mystery event. There was one event that was observed in the Anita 3 project. There was one event that was observed in the Anita 1 project. And now there were 4 more events observed with the Anita 4 data. So the question is, why hasn't the polarity inverted compared to what should have happened? And that has been the subject of extraordinarily a large amount of theoretical speculation. Now, there are a couple of caveats about this that I won't go into in detail. For now, let's just say that this is a mystery which has persisted. If you go to the literature or archive.org, for instance, excuse me, you'll see lots of papers written about the Anita mystery or anomalous events. Okay, I'll mention very briefly in the interest of time that what we did is we put together so here are the 4 Anita 4 mystery events. We put together our own experiment, which was intended to measure the surface reflectivity. So one of the problems with this measurement is that if, for instance, there are regions of the surface which might not be smooth, perhaps those would result in this anomalous signal shape. However, our recent analysis, again, without going into detail, sort of excludes that possibility. Another possibility, for instance, is that this may be a result of the so-called triboelectric effect. So the triboelectric effect is an effect whereby wind blowing over the Antarctic surface or blowing over the snow of the Antarctic surface will produce essentially electric discharges. So this is a static electric discharge effect. It's been known for a long time. In fact, in one of the first experiments that we set up at the South Pole, namely the Rice experiment, we could see very clearly that when wind velocities were very high, we had a larger trigger rate. So we were accumulating lots of events. And again, those just were the result of wind blowing over the surface of the Antarctic ice, resulting in essentially a layer of charge or a separation of charge. And then there was a static there was a recombination of charge, which resulted in a radio frequency signal being produced. What's interesting about this is that there is a threshold for this effect. So the wind velocity has to be about 10 to 12 meters per second for this effect to be noticeable. We looked into the possibility that these anomalous events might be, so here there are 1, 2, 3, 4 anomalous events. We looked into the possibility that these anomalous events might be the result of the triboelectric effect. However, that was ruled out by the fact that those events were collected at a time when the wind velocity was less than 10 meters per second. We're in the process. Well, not we, but the students who are smarter than me that I'm working with are working on producing a model that will try to give us a better handle on what the likelihood is of getting triboelectric triggers. But again, it does not seem that can possibly explain the effect that we're seeing. All right, so that is sort of a summary of one type of technique that's used to detect ultra-high energy neutrinos. And again, the idea in the case of the Anita experiment is that what we're looking for are signals that are produced directly by a neutrino interaction that produces a so-called shower, and you look for the radio frequency emissions within that shower itself. There's another way that you may be able to see the neutrino, at least indirectly. And that's not by observing directly the radio wave emissions from the shower, but what you can do is that you can bounce radar off of the shower. So you have some sort of a radio frequency transmitter, and that transmitter is always beaming signal into the sky or into the ice, for instance. And you can look for the radar returns off of that shower, that so-called shower. And that's the idea of this so-called RET experiment, which we're also involved with. So to test this project, or to test this idea, what we did is we went to the Stanford Linear Accelerator Center in California, and we did a test beam experiment. So what we did is we sent a beam of charged particles. So this comes from the accelerator itself. The accelerator produces a small bunch of electrons. The bunch is maybe a few centimeters long and very, very narrow, certainly less than a millimeter in transverse size. And that bunch of electrons is moving at nearly the velocity of light, and it's sent through the so-called beam pipe. It exits through the beam pipe. It goes through a little coupled device, which provides a trigger to our experiment, and it impacts a target. So this is a high density polyethylene target. It's a plastic target. It has about the same density as ice. And when it does that, again, just as a neutrino would in ice, it produces a shower of particles. This shower consists of mostly electrons and positrons. It does contain some radio waves, but we're not interested in the radio waves that are beamed forward from this target in this particular case. Here what we did is that we had a transmitter. The transmitter was sending out a signal at about 2 gigahertz, and we had a receiver. And what we noticed is that we could actually reflect radio waves off of the charged particles in this shower and have them be observed in the receiver. So, for instance, this is a plot in black, shows a plot of the echo that we observe in our receiver as a function of time. And this particular point at about 8 nanoseconds is when the shower itself, so 8 nanoseconds corresponds to when the shower itself has reached this point and comes into view of our receiver. So the black represents our observations, and we see a clear echo. The blue represents a simulation using a finite difference time domain simulation code, which also shows the reflection. And the red represents our particle level code, simulation code, that not I wrote, but my smarter graduate student wrote, which also very nicely reproduces the effect that we see in data. So we believe that we have a good handle on what this effect is, and perhaps we can use this technique to actually measure ultra-high energy neutrinos in the field, again in Antarctica. This again is a plot of the data. Now the time has been shifted by about 50 nanoseconds. So what we're looking for is the echo at the frequency that we're beaming signal. Remember, the frequency that we beam signal at was about 2.1 gigahertz. And this bright spot shows us the timing of the echo relative to 0 nanoseconds and the frequency. And again, this region is exactly where we expect to see a signal. And the level of the signal strength, again, we tried a couple of different frequencies. We tried 2.1 gigahertz and 1.75 gigahertz with different antennas. And in all cases, we saw signals that matched our expectation, both in frequency and also in terms of the amount of reflected power that we expected. So this is a technique which we think may be promising for the future. And in fact, in 2024, we hope to have our first deployment of hardware. Again, we're going to use Antarctic ice as our medium, construction medium, and we hope to have our first deployment of hardware in Antarctica in 2024. Okay, a couple of future experiments. There's Anita 4 was the last flight in the Anita series. There's a project called Pueo, which has been proposed as a successor to the Anita 4 experiment. This again is the balloon-borne project, and that has sort of been approved at the first level, and that should have higher sensitivity than Anita 4 to both neutrinos and ultra high energy cosmic rays. In addition to that, there is a trailer balloon, as I said before, called HiCal. That's what we're particularly involved with here at the University of Kansas. And that trailer balloon will be launched in conjunction with the Pueo experiment, also around 2024. The RET project, which uses this radar scheme, after we observe this in a test beam, the RET experiment has been approved for first deployment, probably at Taylor Dome, Antarctica in 2024. Now, beyond that, the next big thing in neutrino astronomy is going to be the Gen 2 radio project. So maybe some of you are familiar with the IceCube experiment. The IceCube experiment consists of primarily photomultiplier tubes that detect Cherenkov radiation generated when a munoneutrino produces a muon. The muon travels through the ice and produces Cherenkov radiation. That can be detected in photomultiplier tubes. So it consists of basically 80 strings of photomultiplier tubes. A string is about maybe 2 kilometers long and consists of something like 80 photomultiplier tubes spaced maybe 20 meters apart. Those are in the ice itself, but the scale of ice cube is about 1 kilometer by 1 kilometer. There is a project or a proposal to do Ice Cube Gen 2, which is going to be a big expansion. So instead of having a 1 kilometer by 1 kilometer array, they're gunning for something like a 3 kilometer by 3 kilometer footprint. Now, the Gen 2 radio project is a radio experiment in the ice on an unprecedentedly large scale. So this is a project which will deploy something like maybe 400 stations of radio wave neutrino detectors with a spacing of about 1.5 to 2 kilometers. The total scale of that project is around 400 to 500 square kilometers. So this is an enormous undertaking, specifically in the South, at the South Pole, where logistics are already quite difficult. But this is the next experiment, or this is going to be the sort of the ultimate experiment in radio wave detection of neutrinos. Okay, so that's my last slide. I guess if I were to give you a very brief summary, it would be that that the field has grown considerably. To give you a sense of scale, when we first deployed the Rice experiment in 1996 or 97, it was deployed over about 200 meter by 200 meter footprint. From 200 meter by 200 meters, we've moved to a scale of now something like 20 kilometers by 20 kilometers. So a scale of 10 to the fourth in aerial coverage. And of course, the hope is that with the Gen 2 radio experiment, we'll finally be able to see large statistically significant samples of ultra-high energy neutrinos. And that's all I have. Thanks for your attention.
Thank you, sir, for your wonderful presentation, sir. So if
Sure.
you allow, we can start our discussion session. We have got few questions in inbox. So first, can neutrino help us to find dark matter?
Right. So yeah, neutrinos can help us to find dark matter, and the way that it's done is that so dark matter, as you know, probably better than me, will interact gravitationally. So if there's dark matter, it should have accumulated at places where there are large gravitational sinks. The nearest big gravitational sink is, of course, the sun. So if there is dark matter that has accumulated in the center of the sun, there's speculation that you would have interactions where a dark matter particle will annihilate with another dark matter particle, chi bar annihilation. In that case, there should be some production of neutrinos and antineutrinos. So one of the things, for instance, that the ice cube experiment has done, is that it has looked for neutrinos that are coming directly from the sun at very high energies. Now, of course, the sun produces low energy neutrinos of the order of something like 1 million electron volts. Those neutrinos are too low in energy to be seen by the ice cube experiment. However, dark matter particles, as you probably know, have a expected mass on the order of tens of GeV, maybe 80 GeV for WIMP particles. Those sorts of annihilations could produce in principle, neutrinos high enough in energy, or higher, even higher mass dark matter particles, high enough in energy that that IceCube would be able to see them. So IceCube has spent a lot of time and effort in looking for neutrinos that are coming from the sun as a way of placing limits and constraints on dark matter, anti-dark matter annihilations in the sun. That's the most obvious connection, at least that comes to my mind.
Thank you, sir. We have another question. So, can we detect low energy neutrinos from radio wave technique?
Can we detect what?
Low energy neutrinos. Because here
Low
we
energy
have.
neutrinos. Okay, yeah. That's a good question. So I didn't talk about the threshold, which I should have. So to give you a sense of scale, neutrinos from the sun are about 1 MeV. Neutrinos from supernova are on the order of maybe 10 to the 14th electron volts, or 10 to the 15th electron volts. The energies of the energies that the ARA experiment are sensitive to start at around 10 to the 17th electron volts, so about 100 PeV. Now, if I go back to my first slide, which I think you can still, yeah, you can still see it. So if I go back to the first slide, the process where an ultra-high energy proton interacts with a CMB photon, this is so-called cosmogenic neutrinos. So these are neutrinos produced by the interaction of protons that are too high energy and too far away to be observed directly, but can be observed by the neutrinos that they produced. Those neutrinos, this neutrino over here, I kind of like the fact that I can see this here. This neutrino over here and these two neutrinos have an energy which is about 10 to the 17.5, 10 to the 17.7 electron volts. So we cannot see low energy neutrinos, lower energy than, for instance, 10 to the 17th electron volts. That may change with the Pueo experiment with more intelligent triggering techniques. But right now, we cannot see those sorts of neutrinos. We can, however, see the neutrinos that are left from a collision of a high energy proton, as I said before, with cosmic microwave background radiation. And this is the main science focus of the radio wave technique right now, is detecting these so-called cosmogenic neutrinos. So low energy we can't, but high energy we can. The threshold is mostly set just by thermal noise, the radio wave emissions coming from black body radiation in the ice, as well as the radio wave background from the Milky Way itself. And that sets the lower limit in our measurement threshold.
Thank you, sir.
Sure.
There is another question. I think you have already discussed about that triboelectric effect. So, what is the triboelectric effect? Could you repeat it, sir?
What does the triboelectric effect have to do with this?
Yeah.
Okay. Right. So I'm sorry I didn't make that clear. So the question was, I should have made that clearer. So what we're trying to do is we're trying to understand where these sorts of signals are coming from, these anomalous signals. Remember that the sample of ultra high energy cosmic rays that we have is very small. It's very limited. There are only about 100 of these events. And certainly in other experiments, we know that we can see signals that would otherwise look like neutrinos, for instance, that happen at times when the wind velocity is very high. So the reason I tried to say something about the triboelectric effect was to offer this as a possible, so you're trying to understand why this signal has this anomalous polarity, why it predominantly goes down instead of going predominantly up like it should for a normal reflected cosmic ray. And one of the things that might occur to you is, well, maybe it has nothing to do at all with cosmic rays, and maybe it's just a result of some meteorological effect, such as the triboelectric effect. So that's why we investigated this. We investigated a number of different glaciological explanations, in fact, and we excluded them all. So it's not a result of wind-generated radio frequency backgrounds. It's not the result of ridges in the surface. It's not the result of the fact that there are real cosmic rays and somehow the surface topography leads to this anomalous shape. It's not the result of embedded reflectors. So sometimes there are ash layers in the ice itself. It's not a result of that either. So the triboelectric effect I mentioned in the context of those alternate explanations.
Thank you, sir. This may be the last question. So,
Okay.
sir, can you detect the reactor neutrino using this technique?
No. So reactor neutrinos are, again, much too low in energy to be detected. This is only appropriate for really ultra high energy neutrinos that are coming from beyond the Earth.
Yeah, thank you, sir, for your wonderful presentation and discussion session, sir. So, I think our students have learned a lot of things about this new technique of neutrino detection. So, the main aim of our program is to motivate in this corona pandemic situation, and we are trying for that thing. So, and I'd like to say thanks for accepting our invitation, sir. So, it's my
You're very
honor
welcome.
and privilege, sir, to host you in our international physics webinar.
You're very welcome. And if anybody has any questions, you can find me online and just email me.
Yeah, of course, sir. As the video will stay remain in YouTube and Facebook, so if somebody asks question, I will send to you, sir. And
Okay, that sounds great.
Okay, sir. Thank you. Bye for today, sir.
Okay, thank you. Okay,
Thanks.
have a good day.
Yeah.
Bye-bye, y'all.